Okay, so now we're going to talk about an example of an important sort of matrix manifold, which is called the Stiefel manifold. Okay, so this is an embedded submanifold of R n cross P, so the orthogonal Stiefel manifold. It's an embedded submanifold. Of R n cross P, which shows up regularly in applications. Okay, so it's denoted as the following: ST Pn, right? So where P is less than or equal to N, right? Is the set of all N by P orthonormal matrices. So the way to sort of think about them is that you have P n vectors, that's like which are orthonormal with respect to each other. Okay. So this basically means that STPn, the set of matrices, n by P matrices, with the property that X transpose X is the P-dimensional identity matrix. Okay. It's the P by P identity matrix. Okay. And then if you endow this, it's like with the submanifold structure. This set with the submanifold structure. Right, refer to this then as the orthogonal or compact Stiefel manifold. Okay, and then so this is going to be distinct from the non-compact Stiefel manifold. So this is distinct. Which is R star n cross P. Okay. All right. Anyway. So it's clear that this is a subset of R n cross P, right? And then there's a linear manifold structure on R n cross P, which is sort of the obvious thing. It's like where you just look at the entries, it's like of the matrix, and you think of that as a coordinate chart, right? Okay. So now what we're going to do is that we're going to show that this is a embedded submanifold. It's like by using the sort of submersion theorem. Okay. So in order to do that, we have to find a map from Rn cross P into some other space that's like such that this map is a submersion. Okay, so let's consider the following function. Consider the map F from Rn cross P to this set of symmetric matrices of the dimension P. Okay, and the way we do this is to map a matrix X to X transpose X, right, minus the identity. All right. So, so this is obviously motivated. It's like by this condition here, right? So what's going to happen then? We can check that this is symmetric, right? It's symmetric by construction, right? X transpose X is always symmetric. The identity is symmetric. The difference of symmetric matrices is symmetric. So that's fine. And then obviously this Stiefel manifold is the preimage of the zero matrix, right, of this map. Okay, so that's sort of the natural thing, right, where, again, S sim P is the set of P by P symmetric matrices. Okay, and you can check that that's a vector space. Okay, so you don't have to worry about the use of charts, basically. Okay, so clearly Stiefel Pn is F inverse the P by P zero matrix, right? So we just need to show that F is a submersion at every point. X of this Stiefel manifold. Okay, so you can check that d of f of x in the direction z, okay, is going to be x transpose z plus z transpose x. And then you can also check that if you take this and you let x be 1/2 x c hat, this is c hat. Okay, where c hat is a symmetric, is this it's an arbitrary symmetric matrix. Okay, so we're trying to show it's a submersion, right? So we want to show that it's onto, basically. All right, so so that's basically what happens. So this means that the F is full rank. Okay, and then by the submersion theorem, right, the Stiefel manifold Pn is an embedded submanifold of Rn cross P. Okay. And then if you recall, it also tells you something about the dimension of this embedded submanifold based on the difference of dimensions between, so I should say that F, if you recall, was a map from Rn cross P to the space of symmetric matrices of dimension P by P. So the dimension of the Stiefel manifold is equal to the dimension of Rn cross P minus the dimension of the symmetric matrices of dimension P. Okay, so this is just n times P, right? And then this is the P by P matrices. So again, if you think about it, if you have a P by P matrix, right, the diagonal is free. It's like, and then you have the sort of upper triangular part. So if you just specify those two, it's like then by symmetry, it's like you get the lower triangular part. So the only freedom you have is the diagonal entries and then the upper triangular pieces. And so that has dimension 1/2 P times P plus 1. You can check that easily. Okay, so that's the dimension of the Stiefel manifold. You can also check that the manifold is compact. And then there are sort of two limiting cases, right? When P is equal to 1, right? This Stiefel manifold N1, right, is equal to just a unit sphere as n minus 1. And then when P is equal to n, Stiefel manifold N, sorry, I guess the convention is P first. Yep, okay, is just the orthogonal group of dimension n. And then dimension of this is just 1/2 n times n minus 1. Okay. All right. All right. So that finishes up our discussion. It's like of embedded submanifolds. It's like in this sort of is a particular example of this where we showed that it is indeed an embedded submanifold by using the submersion theorem. Okay. So let me just stop here for now.